Thank you. Okay, good morning. So I'm Chenxing, and I'm from Shanghai TreeGraph Blockchain Research Institute. And today I'm happy to be here to introduce our research about the heterogeneous blockchain framework with interoperable virtual machines. So because currently, so in the blockchain world, there are many different virtual machines, such like the Ethereum VM, the MoveVM, the Solana VM, and there may be some other virtual machines. And these different virtual machines, they have the different programming language, different development tools, different SDK suites, and different wallets. So these differences divide the users and assets into different ecosystems and make this ecosystem be fragmented. So why people want to choose the different virtual machine? Because each virtual machine has their own advantage. So the EVM, the earliest and now it also has the largest smart contract ecosystem. It has the many existing development libraries, and it is the most mature ecosystem. And also, EVM have an overwhelming advantage in terms of the proportion of the asset deposits and the user shares. But the earliest also means the legacy design and technical debt, because when people design the EVM, they don't know what the smart contract platform will be and what the smart contract will be used for. So it have many legacy designs, maybe not suitable for the current application. And some new virtual machines, such as the Move, they in their design, they have many modern designs which gives the native support for the assets for the financial applications, such as the formal verification, the safe ownership, and the resource-oriented design. However, the application developers usually choose the EVM because of the market consideration. So what we want is to build a unified blockchain that runs multiple interoperable virtual machines. So in such an architecture, we have multiple virtual machines in one blockchain framework, and each virtual machine will have its own RPC module because it needs to retain the compatible with its existing ecosystem. And each of their RPC module will receive the transactions in this system, and there will be a unified consensus layer to put multiple types of the transaction from multiple virtual machines together and to reach the consensus. And in the execution step, so the execution module will dispatch the transactions to different virtual machines according to their transaction types, and the virtual machines will update the storage accordingly. But here, what we want is not only to put the multiple virtual machine in one blockchain framework. What we want is also the interoperable. We want the transaction, no matter in which virtual machine, they have the availability to execute the contracts in the both virtual machines. They have the ability to cross the virtual machines in one transaction. So here is a challenge because the different virtual machines, their language have many different design concepts. For example, the way for the permission control. So for the Move language, so if there is a function and this function needs some special permission to call with that, the Move design is to define a special struct and require an instance of this struct. So anyone who can provide such an instance, they have a permission. So because Move is a resource-oriented language design. But the EVM have a very different design because in the EVM, the system will provide an API. So the smart contract developer, they can read this message sender address from the system API, and the function will write its own logic to decide whether this sender is acceptable or not. So another difference is the parameter. So in the Move language, there are many language virtual machine level design support for the concept of the functions, parameters, types, and even for the generics. But for the EVM, so at the virtual machine level, they do not have any concept of the function. They are only just merely raw data, a chunk of data. So if we have the virtual machines, the transaction execution in the different space, we need a cross virtual machines translation module in the middle to translate between the two different virtual machines so that the function calling from one space could be understood by another space. And such a transaction translation module will provide the system API for the virtual machines. And with such an API, we can achieve the cross-space invoke and handler. So this diagram shows that how this works. So first, for each space, we have a system API for the cross virtual machines module, and when the developer wants to define their own logic for the cross-space interaction, it will deploy a invoker contract as a home space and deploy a handler contract in another space. So the invoke contract will call the system API, and the system API will translate this call in a format of another language, another virtual machine, and call that handler. So both the invoke contract and the handler contract can be developed by the tools from the corresponding virtual machines. They are fully compatible. Because here, what we do is not to change any language features. What we do is just introduce two system APIs. So with such underlying support, we can support some application level needs. For example, the cross-space asset transfer. So we have deployed the cross-VM handler and the invoke contract for the token asset. You can think this is a standard library based on our system API. And in this process, when a user wants to transfer the asset from the pair contract, and it will to notify the cross-VM smart contract. And after the cross-space call, the handler contract will pass the corresponding message to the contract deployed at another side. And the most important thing is that, so because all these things are inside one transaction, it means that if any step in the middle fails, so all the side effects from the both space, the EVM or the MoveVM, will be reverted atomically. And this diagram shows another process. It means that so claim the asset from another space. Now, since we have the availability to send the asset from one space to another space, or claim the asset from another space back to this space, so we can achieve the cross-space, we will try the cross-space DeFi interaction. So this is the whole interaction flow. So here, we deploy a PancakeSwap official Move implementation at the Move side. And based on this process, we provide a standard Uniswap v2 solidity interface. It means that for a project, for application project, they can choose their language. For example, the Move language, it has modern design, it may have a better security guarantee, and may have a better performance to deploy their product. And their product with this framework can also serve the whole EVM ecosystem. So this interface is compatible with the existing EVM ecosystem such as the wallet, the existing smart contract, and the SDKs. So we can achieve that. So you can develop your product at one space and provide a service in another. Maybe it is more mature and have more users this space. So we have implemented such a system. So our implementation is based on the Aptos. So Aptos is a MoveVM blockchain. So we have a MoveVM first, and then we integrated an EVM engine into the MoveVM. It is a Conflux VM because we are from the Conflux team. We are more familiar with our EVM implementation, and there are some other implementation details. Let me skip that. So in our evaluation, we first want to check whether the introduce our new features influence the performance of the existing features in the Aptos. And the results show that we only introduce only a few overhead compared to the standard Aptos implementation. So it means that the new feature will not influence the existing features. And in this graph and in this diagram, we have tested many different tasks for our framework. So this task, so for each task, we will first consider about we deploy a service at one space, and we want to show that what is the performance, what is the throughput to serving the user in the same space or serving the user in another space. So the first point is that the token transfer as the Move virtual machines. In the Move virtual machines, we can show that the token transfer for the native coins and the token transfer for the custom coins inside the same space is similar. So because the Move language has the exactly same implementation for these two types of coins, but for the EVM, the native token transfer is much faster than the custom token transfer. So we can see that for the native token transfer, the cross-VM implementation, the cross-VM throughput to serving the user in another space will have a similar throughput, but for the custom coins, there will be a significant performance drop. And for the next part is the token transfer as the EVM. So because the EVM is much faster, so we can see that the native token transfer have a significant throughput, and the custom token transfer have some performance drop. So because for the standard implementation, the EVM token transfer is much faster than the Move. So when we see the performance of the cross-VM implementation, we will see that the performance will be dropped significantly because the official implementation of token transfer for the Move language is more complicated than the EVM. And also, so for the cross-VM implementation, we must to reuse the Move official implementation. And next, there is maybe some interesting insight is about the DeFi, the Uniswap performance. We deploy the PancakeSwap official implementation at the Move side, and we also deploy the official Uniswap performance at the EVM side. These two DeFi products have a very, very similar functionality and have the same product logic. And we can see that when we serving the user from the same space, the Move implementation is slightly higher than the EVM implementation. This may be indicated that for the complicated financial applications, the Move language have a better performance than the EVM, and it also have a better security. And when we see that, when serving the user from another, space, we will see that the performance is about 1/3 compared to the user from native space, because we have many overhead from the cross-VM handler, from the token transfer, stuff like that. So there will be a performance drop. And for the future work, there is an interesting point is worth studying is the economic model. So because for a blockchain system, each block have a capacity for the computing resource. So if there is only one virtual machine, the result is trivial. But if we have multiple virtual machines, things become tricky. So should we give a fixed resource allocation for the different virtual machine, or should we introduce some dynamic bidding model for things of that? And another point is that, so this is what really happened on the confluent mainnet is a cross-space arbitrage. So if we have multiple virtual machines, if one virtual machine have many users and use needs and makes the transaction fee is expensive, and another virtual machine is cheaper than the first virtual machine, people will use the cheaper virtual machine, use the cheaper space, and use the cross-space call to interact with the expensive space to obtain the transaction fee. So is it an acceptable behavior, or should we disincentivize such a behavior? So there are some small decisions require some insights from the econ or the gaming theory. So as a conclusion, we built a unified heterogeneous multi-VM blockchain framework, and it have a good performance and with fully toolchain compatibility. Thank you.
Okay, for your questions, please come up to the mic. Yeah, So I have a quick question. So my impression was that a lot in the smart contract space is about formal verification of smart contracts, and now you're going between blockchains. Is there also a story about formal verifications?
You mean, yeah, so I think related to the formal verification of the multiple VM is a more challenging topic, and we also regard it as a future work. Yeah.
Right, thank you.
Okay.
Any more questions? Then let's thank the speaker one more time.
Okay.